1.1 Four ways to represent a function. Um, this is going to be a recall sections for us, and as well as 1.2, 1.3. Okay. So in previously, like we learned functions, and we know that functions can represent in verbal, numerical, visually, and algebraically, right? Which is like, in wordings, tables of values, graphs, and in formulas. So we want to review a little bit on these sections about the functions. So definitions of function. Function is simply saying there is a domain, right? And mapping to range with a certain formula. Function is a formula, right? But what we know is every elements in the domain, right, map exactly one element in a range, and we define that as a function. So on a graphical part, it's easier to identify which is a function. For example, if I have a curve like this, right, and I can name this as a function f, right, and we can simply use a vertical line test to see this is a function or not. If a vertical line passes through the graph only once, no more than once at any point, then we call that as a function. And for example, if I have some function, something like this, okay, then you can see that in this functions, the graph of functions, the vertical line, at some point, the vertical line passed through more than 1 point. So this is a vertical line test, that you can use to identify the graph can be considered as a function or not. The next step is quickly to review on evaluating the function. And evaluating the functions is simply substituting the values and evaluating, right? Substitute the value into the formulas and evaluating it. So let's take a look at on the first example when the function is a quadratic and we want to evaluate at -3 and 0. So let's try to substitute and evaluate that. So when we substitute -3 into the formula and then evaluate it, you can use calculator or mental math. Then this will give you 17. And when you evaluate 0, right, substituting into the function formula with 0, then you will get -1. So this is evaluating a polynomial functions. And next up, let's take a look at on evaluating the radical functions. And let's try to substitute and evaluate it. So when you substitute 5 into the formulas of g functions and then compute it, we got 4. And when you substitute g into the g functions, the formula of g functions, -3, then you can see that under the radical, you have a negative value, which we already know this is a complex number. So therefore, it is not a real number. And the purpose of this example is going to be helping us to review on how to find the domain of the radical functions in later examples. Now, let's take a look at on next example, example number 3, evaluating the rational functions. And we're going to be evaluating at -2, 0, and 2. And let's try to evaluate that. So on the first problem, when you're evaluating at -2, and in the denominator, -2 squared plus -4, that will give you 0 in the denominator. Right? So it'll be -2 over 0, and we know that this is undefined. And when you evaluate at 0 for this function, we substitute 0, and when you compute it, 0 over -4, so which is going to be what the value is 0. And finally, lastly, when you substitute 2 into the functions, into the formulas of the function h, then we got, again, same as the first part, which is 2 over 0, and this gives us undefined. And hopefully this example helps you to recall that if you have irrational functions, you have to be careful with your denominator, what is your input is, right? Because when you input it, the denominator cannot be equal to 0. And that's going to help us to find out the domain of irrational functions in later examples. Now, this is evaluating functions. So let's take a look at on the next part. And this is something that we did in pre-calc, right? And this is also a crucial algebraic part that you need to know how to simplify for any type of functions, right? Uh, in this case, I'm giving to you a function k for x squared minus 3x, and we want to find out the difference of quotient. So the difference of quotients, the formula is k of a plus h minus k of a all over h. And on the this is a formula that you want to remember, okay? Because on the test, I may not give you this formula, and I will just simply say that find the difference of quotients. So you need to remember the terminology along with this formula. And we're going to use this difference of quotient formats a lot once we start talking about the definitions of derivatives, right, in chapter 2. Along with the limits idea. So let's review on how to simplify this difference of quotients formula. So first, what we will do is we will find out this, evaluate the functions at a plus h, and then k of a. Right? So let's try to substitute into the functions. Here's the different quotients, k of a plus h minus k of a over h. And let's plug it in into the formula, right? The functions k with these input value. So substituting a plus h into the functions, and this is what the first portion that we got. Make sure you write it with the proper grouping symbol so that you can simplify clearly and without mistakes. Right? And also in the minus with what k of a. So we substitute the variable a, right, into the formula of functions k, and this is what we got. Now what we want to do is we want to simplify the numerator and then try to continue simplifying this fractions. And let's try to do that. So foiling a plus h to the second power, that'll give you a squared minus plus 2ah plus h squared. And then distributing -3, that'll give me -3a minus 3h. And then simplifying the second grouping symbol, it will be a squared minus 3a. Now let's try to distribute this negative into the second grouping symbol and then combine like terms. So when you distribute a negative into second grouping symbol, that will become negative a squared plus 3a. And combining like term a squared and a squared becomes 0. Negative 3a plus 3a will become 0, which will result in 2ah plus h squared minus 3h. And what we can do right here is factor out h and then reduce it with the denominator. So that way we will get our final answer. So our final answer in this case is 2a plus h minus 3. And this is simplifying difference of quotients for this particular functions. And as I mentioned earlier, you should be able to, simplify this difference of quotients with any type of functions: radical, rational, absolute value, so on and so forth. Okay. Now, moving into the next step, is domain of functions. And we know that, simple linear functions, quadratic functions, cubic functions in general will be polynomial functions. The domains are all real numbers, right? So we don't really need to do a lot of work. And absolute value functions, okay, the domain is all real number if the inside of absolute value is, a polynomial, right? And radical functions, we already indicated earlier, right? Radical functions, what you need to be careful is the radicands must be greater than or equal to 0 when the index is even, right? If the index is odd, then we can simply know that this will be what all real number, unless your radicand has some other restrictions, which is a compensations of function. Okay? We will talk about more on that later. Rational functions are fractions. So we know that rational functions, the main thing that you need to focus on is the denominator cannot be equal to 0. Right? So we can basically look for the values that gonna make the denominator 0, and then discard all of those input values from the domain. And lastly, the trigonometric function, sine, cosine functions, the domain is already a number. Those are straightforward one, right? Simple one. And then the tangent functions, the domain, you need to remember that the first one period of tangent is from negative pi over 2 to pi over 2, and there negative pi over 2 to pi over 2, at the negative pi over 2 and then pi over 2, they have vertical asymptotes. Right? So this the tangent functions and other trigonometric functions are periodic. They have like vertical asymptotes. Right? So your domain will be a restricted, which in this case will be 2n plus 1 pi over 2 in general. Right? The exponential functions, domain is all real number. And the logarithmic functions, you need to remember that the argument has to be greater than or equal to 0. Any x value that's going to satisfy this inequality will be considered as part of the domain. And these are, ideas of the domains of some of the fundamental functions that we learn, right, from the previous up to previous course. So now let's try to take a look at on the examples of it, and then some of the example I try to combine things so that you can see what we need to consider. Right? So for the part A, and I can see that this is a radical functions with an even index. So according to the what we learned in theoretical part, radicand must be greater than or equal to 0. So any x value that satisfies this inequality we'll consider as the domain of these functions. So in this case, our radicand is 3x minus 1. So solving for it, which is x is greater than or equal to 1/3. And that gives us now the domain of my functions, right? In the interval notation will be a bracket from 1/3 all the way to positive infinity. So you should be able to write in interval notations, set builder notations, right? And so on and so forth. Here's a set builder notation just in case we forgot a set of x such that x is greater than or equal to 1/3. Close set. Next example is a rational functions, but the rational functions with in the denominator I have some absolute value functions. So we know that in rational functions, what we need to consider is the denominator, right? So what we consider in is denominator cannot be equal to 0. So technically, what we can do is we can use a systematic way to solve it. For example, I can say the absolute value of x plus 1 cannot be equal to 0. And I need to look for any of the x value and then discard that from the from the uh, domain. Right? If I'm doing systematically in this problem, I will be solving for absolute value of x. So it'll be absolute value of x cannot be equal to -1. And we clearly see that there is no solutions right here, because absolute value of any number will give you a positive outcome, and a positive outcome cannot be equal to a negative outcome. So therefore, none of the the value of x in a real number will satisfy this equation. So therefore, in this case, there's no solution. And which means we have no value of x needs to be discarded for the domain. So another way of saying is, for this rational function, domain is all real number. So now I can indicate that domain of function g, that would be what? All real number, which is -infinity to +infinity. In a set builder notation, will be a set of x such that x is all real number. Next up, in example number 3, finding the domain. And for this problem, we're going to be reviewing some algebraic solving techniques. Right? And this is very similar to example number 1, because we are talking about both of them are what? Radical functions. Okay, but the difference is the radicand part. The radicand in example 1 is a linear, but however, the radicand in the example number 3 is a quadratic. So that's the questions, how do we solve for this quadratic inequalities? Okay. So being said that, like before, according to the conceptual part, since this is an even index, the radicands must be greater than or equal to 0. So in this case, the radicand is what? X minus 3x squared. So we are looking for any x value that satisfies this inequality, which means that's the domain for this function. So how do we solve this quadratic inequality? So we factor it out. That will give you 1 minus 3x, which will allow us to easily find out the undefined and then zeros of this polynomial. So in this case, I have 0. The value of 0 will be x is equal to 0, or x is equal to 1, -1/3. Right? Because if these two values, when you substitute in, that will become 0. And undefined, and next thing is we need to find out undefined. And in this case is what? None. Right? The polynomial has no undefined. So this is the first step of solving the radical functions. Right? I should say, let's put this as this first step right here. If you can factor it out. And then this will be the second step, right? Which is finding the zeros or undefined, which we call it the critical points. And the reason why we need to find out the critical point is, hopefully by this time you recall already, we need to break down the intervals on a real number line using these critical points, which in this case is 0 and 1/3. And right away, you need to consider these critical points are part of the answer or not by looking at your inequality symbol. In this case, it's greater than or equal to, so therefore it is what? Inclusive. And that helps us to break it down into interval 1, interval 2, and interval 3 on the real number line. And what we do on the next step, step 4, is basically testing on each interval by picking a number. And what are we testing? Because we want to find out the solution for this inequality. So therefore, what we will be substituting into inequality and see does it satisfy or not. So this is the process of solving this quadratic inequality. The conceptual part of finding out the domain of radicands, radical functions never change, which is always what? The radicand must be greater than or equal to 0. But depending on what type of radicand do we have, that's where we need to use like algebraic. We need to remember algebraically how to solve those. And that is the purpose of this example to recall, right? So now being said that, I'm going to pick -1 on this interval 1, and then I'm going to pick, this is 1/3, so it's 0.333. So let's say I pick 0.1, okay? And right here, the easier numbers, I will pick 1. And then what do? We can substitute into this inequality or this inequality to solve it, to check. And the easiest is like, put it into a factor format so that we can just check the sign and then consider if this is true or not. Okay. So when I plug in a -1, that will be -1 right here and then -1 right here, right? When I plug it in. So this will give me the first factor is negative. And because of a negative, this become positive. So it will become what? This is a positive. The second factor, the result of the second factor is positive. A negative number times positive number is a negative, right? That's what we got. And we know that the negative value cannot be greater than 0. So therefore, this first interval is not part of the solution. Similarly, I'm going to do the same thing for the next one. When I plug it in -0.1, this will be a positive. The first factor result is positive. When I plug it in 0.1, that will be 1 minus 0.3, which will be also a positive result. So positive times positive is a positive value. And then we know that a positive number is greater than 0. So therefore, this is a solution. Right? This interval is a solution. And lastly, I'm going to check 1. When I substitute the third interval, when I substitute 1, that will be a positive value. And when I substitute into the second factor, and this will become a negative value because 1 minus 3, that will give me a negative. So a positive number times a negative number, that will give me a negative result, and which we already know that negative number that's not greater than 0. So therefore, this cannot be a solution either. Now that I found out what is the solutions of this inequality, then we can talk about the domain, because domain are any x value that's satisfying this inequality. So in this case, finally, I can conclude my answer. Domain of functions f, that will be from 0 to 1/3. And then make sure you put down the brackets on each of the cases. Okay? And that will be the interval notations for this function. And set builder notation will be a set of x such that, and since this we are talking about the value between these two, so it will be x is greater than or equal to 0 and less than or equal to 1/3, and close set. And this will be my answer for this particular one. So this example shows that the conceptual part doesn't change, but however, the algebraic part of solving you need to know. So the last example is rational functions, but the rational functions with including, right, the trigonometric functions in here. So the conceptual part, okay, for finding the domains of the rational function is as before, denominator cannot be equal to 0. Another way of saying is we want to discard all the, x value, which will give the denominator 0. So substituting the denominator and then solving it, which is another way of saying that we're going to be solving for a trigonometric function equations. It is very important that you review your trigonometric equations, right? Trigonometry part, because we're going to be using a lot, and it is necessary that you need to know how to do them very quick. So solving this will become sine of 2x cannot be equal to 1, because when I subtract 1 and then divide it by -1, that's what we got. And from here, we know that sine value is 1, right? When the angle, which in this case, my angle is a double angle right here, is pi over 2, 90 degrees. Okay? And what you want to do is you want to write it in general, because sine is the oscillation periodic functions. So in general, that will be what sine is a 2 pi periodic, so plus 2 pi n. And now I can solve for x, which is going to become divide everything by 2, right? So this will become pi over 4 plus pi n. And whenever the n is what? The integers. N is equal to 1, 2, I should say that 0, 1, 2, 3. I should say, let me put it this way. N is integers. That's a notation for the integers. So finally, I can talk about my domain in this case. Domain of the function g, right? That will be, it's easier, the best to write in a set builder notation in this case, which is we will be talking about what set of x such that x cannot be equal to pi over 4 plus pi n, and where n is the integers. Okay, and then close set. So remember, this is the notations for integers. Z with double bar. Okay, if you've never seen it before, that would be like, you know, a real number with R with double bar. Okay, so these are you know, these example hopefully, you know, help you to reconsider, right? Reviewing on the algebra part, on any type of solving any type of inequality, any type of equations, and trigonometric identities, solving trigonometric equations. Okay. Next step is looking at the graphical graph of the functions, reviewing. So I'm giving to you, like, you know, some fundamental graph of it. You can see that y equal to x squared, which is a parabola, is not shifted yet. We call this a parents graph. So I'm basically giving to you, you know, recalling the shape of the parents graph of certain functions: x squared, x to the cube functions, rational functions, 1 over x, radical, square root, cube root, absolute value, natural logarithm, exponential, right? And sine, cosine, and then tangents. So those are the shape of the graph of some parents graph of some functions that we gonna get in handy later on. Right? So definitely you need to know how to recognize and then use the transformations to graph, okay, whenever it's possible. Now, I did not put it, notice that I did not put it the secant, cosecant, and then cotangent, because those are basically what you can get it from the sine, cosine, and tangent. Right? And if you need help on those to, you know, when you're reviewing it, please ask me. Okay, don't hesitate to ask me any questions. Next, from here, what we see is, like, you know, parabolas, cube root, rational functions, absolute value functions. And there are some symmetrical in here, right? This is symmetrical about the y-axis. This is symmetrical about origins, these two, this one, and this is symmetrical about the y-axis. So that has something to do with the even and odd functions of, you know, the function. So that's what we want to look at it in the next case. And we call it is even functions when we substitute a negative x into the functions, and then after simplify it, and the simplified function is exactly look like the original functions, then we call it as an even functions, and the even function is symmetric about y-axis. Okay, even function is symmetric about the y-axis, and all functions is the same thing, the same process. We substitute negative x into the functions, and the outcome is a negative, extra negative factor with the original functions, right? Original function has extra negative factor. Then we call that functions and odd functions, and then the odd function has a property of symmetric about the origins. And that's going to come in handy once we go into chapter 3. We're going to be using the calculus approach to graph, you know, a lot of functions. And this is going to help us to, speed up on graphing, I would say, right? So let's take a look at on like determining even and odd functions for the next two example. So being said that, what we're going to do is we're going to substitute, right, the original functions with negative x and then see what do we get. So let's try to simplify that. So when you substitute negative x into the functions, right, and then evaluate it, simplify it, that will become negative x to the third power over x squared plus 1. And this is simply, a negative factor with the original functions that we have. So we are talking about getting into this situation, negative f of x, right? Because this whole portion is just a function, original function. So that basically indicating this is a function, this is an odd function. So now I can determine that f is an odd functions. And right away, we know that odd functions are symmetric about the origin. So their graph will be symmetrical about the origins. Okay? So that's the usage of that. Now, let's try to take a look at on example number 2, which is, again, substituting the g function with negative x. And let's try to simplify that. So when I substitute negative x into the g functions and then simplify, I got negative 2x minus x squared. And this is not original functions, right? This is not original functions, so therefore it cannot be the first case even functions. Then to think about is an odd function or not, I'm going to try to factor out this negative, so which is going to be negative times 2x plus x squared. Again, this is not negative of the original functions either, because this is not minus right here. So therefore, in this case, this does not satisfy the first case nor the second case in the definitions that we have. So therefore, this is a neither function. So I can say that therefore g is neither even or odd function. So meanings we don't know anything about is symmetrical about YLSS or original at all. Right? So we're gonna have to use a different, method to graph it a lot better. So this is a recall of even and odd functions. Now going into increasing and decreasing functions. And this is basically the, definitions out from the algebra class. And then once we get into using technique of calculus, it will make it a lot easier and clearer to determine which intervals is increasing or decreasing of functions. So it is basically saying a function is called increasing on a certain interval I if the y value, right, is increasing steadily as x increases, right? So that's what this inequality means. So for example, if I have something like this, right, and if I want to take a look at on this interval from A to B, and you can see that every y value is what? Increasing, and as x value is increasing between interval A and B. So this is the increasing intervals in here. Now, as we look at in the next one, which is from, interval from B to C, right? Interval from B to C. And let me denote it with the blue right here so that you can see better, right? So this is the increasing. And the next one, if I use this, this region right here, interval right here, and any x value between B and C, the interval B and C, you can see that the function value is decreasing, right? Smaller and smaller as what the x value increases. So this is called the decreasing interval, right? So this is basically straight out from the definitions in algebra. But the problem is, as we have before, only if I can see the graph, then I will be able to tell which intervals are increasing and decreasing. and I'm not really sure how to do algebraically and how to find out algebraically at this point. Okay? So that's we're gonna stop. We're just gonna stop right here for this until we learn more about ideas in calculus and then try to find out increasing and decreasing interval. That will be like in chapter 3 that we're gonna be looking into. Okay? And last graphical part that we want to look at is the piecewise defined functions. Right? We learned how to graph it. Now we want to review it. A piecewise defined function is basically a functions with a multiple formulas, and each formulas are restricted in a certain part of the domain. So it's not entire domains, right? Only restricted in a certain part. So if you take a look at on the first example, f of x is equal to x plus 1 if only x value is less than 0. So any x value that's less than 0, if you want to evaluate it, you need to use this part of the first part of the formula of this function. Okay? And if you're gonna be talking about the x value in the interval of 0 to 2 as well as 2, right? Then you're gonna be using the second formula right here. So it is important for us to know how to evaluate a function so that we can graph it and then talk about the domains. So let's try to evaluate these functions, which is evaluating a functions of -3. The input -3, right? And we have to decide which part of the formula that we need to use. Since 3, okay, you can basically check this way. Since -3 is less than 0, that is what a true statement, and therefore I will be using this formula to evaluate the first part of the functions to formula to evaluate for this function. And you can clearly see that 0 is less than -3 less than or equal to 2. This is not a true inequality, right? So another way of saying is you don't need to plug it in. I'm just showing to visualize it. At this point, you should be able to read how to read the inequality, right, symbols. So being said that, now we're going to substitute -3 into the first formula, which is -3 plus 1, and which give us what? -2. That will be the answer. And the next is evaluating f of 0. So when I take a look at and then determining which part of the formula that I need to use, I have to go back to the restricted domain again. The first part of the formula is telling us only if the value of x is less than 0. So it's not including 0. So I cannot use this formula to evaluate this f of 0. Now, when I look at the second part of the formula, x squared minus 4, this formula can be used when x value is between 0 and 2, including 2, but not 0. So from this restricted domain, the 0 is not part of the domains. So if it is, if the input is not, the input that we are evaluating is not part of the domain, there is no outcome. So in this case, what we call it is what? Undefined. Okay? Once again, 0 is not in the first part of the restricted domain, nor the second part of the restricted domain. So therefore, I cannot evaluate these functions at 0. And lastly, evaluating f of 2. And you can see that the first formula is restricted what? On x value that is less than 0. So 2 is not less than 0, so I cannot use the first formula. But I can use the second formula because the restricted domain is between 0 and 2, including 2. Right? The x value is including 2. So therefore, I can substitute 2 into the second formula. So 2 squared minus 4, which will give us 0. So that's how you evaluate the piecewise defined functions, making sure that you know how to check your restricted domains. So quickly with this example, the next one that we want to look at is what is the domain of this functions. In a piecewise defined function, domain is already given to you, right? So you just need to know how to combine them. So the first part of the formula tell us that everything between less than 0. So I can get anything less than 0, right? That's part of the domain. And the second part of formula allow us to use that to compute any value between 0 and 2, and then 2 is inclusive. So on a real number line, I can sort of visualize like this. And then from here, I can tell about my domain already from this real number lines. So domain of f is basically what? From negative infinity to 0, but not including 0. Union with 0 to 2, right? 0 to 2, and then 2 is inclusive. So the restrict in a piecewise defined function, you know, the domain is already given to you. You just need to know how to combine them. And lastly, what we want to do is we want to graph this piecewise defined functions, right? So we know that it's going to be up to only 2 and then anything below. So let's draw the x-axis and a y-axis, right? And then make sure you scale them, right? So let's graph the first part of the functions is a line, right? X plus 1. So we have y-intercept at 1, and then the slope is 1. So it will be, here's 1, right? Here's 1. But you need to remember that x is less than or equal to what? 0. Right? So you cannot have at 0. But however, what we need to do is we need to make sure everything is included. So it'll be what? A whole, an open circle at 0. And then we're going to talk about, the graph of it, which is what? The slope is go up 1 and right 1, go up 1 and right 1, or go down 1 and left 1, so on and so forth. But we don't graph any positive portion of it, so I'm going to erase that, and then our graph is going to be look like this, because the domain for this first formula is restricted from what? 0 and then less. No, not including 0. I should say less than 0 only. So that will be the first portion of the graph. Now, graphing the second portion of the graph, this is basically a parabola shifted down 4 units. So I know that the parent's graph of parabola is at 0, 0, right? And then I'm going to have to shift it down 4 units. So this graph is going to look like this. But however, we know that our graph is the domain for this formula is only between 0 and 2. Right? And then again, 0 is not included. So therefore, this left side of the portion of the graph will be gone. And then at negative 4, it must be open circle. And then we need to find out where is the 2, 1x is 2, what is the function value is. So to talk about this graph, I'm going to use this. So at 4 will be what? Open circle. At negative 4 will be open circle because the graph shifted down 4 units. And then we know that when f of 2, the function value is 0, which is in this case will be what? A closed circle. And I cannot go any portions on the right side of this 2 because the restricted domain is only from 0 to 2. So therefore, when I graph this, this will be a parabola shape like this, and then stop right there. So that's why it's very important that your endpoints are open circle, closed circle, or is arrowhead, right? Because arrowhead indicate that it's going to continue going to the left or continue going to the right and then going down or up idea. So on the test, I will be paying very close attentions on these endpoints. Do you put in correctly or not? So you need to really know how to look at your domains from this original given part, this restricted domain. Okay, and that is the example for a piecewise defined functions. And next example is also graphing this piecewise defined functions. And take a few minutes to start working yourself and then see, do you get the same answer as me or not? Right? So when I'm evaluating f of -5, this input -5 is in the restricted domain of the first formula, because the first formula go along with the restricted domain of anything below -1. So therefore, I'm going to be using the first formula. So when I evaluate this, -5 plus 3, -2, absolute value of 2, 2 minus 1 is 1. That's what we got. And for the first, second ones, right, the restricted domains is on the second formula, which is the input is in the second restricted domain, right? Formula of second restricted domain, which is between -1 and 3. So I'm going to be using the second formula, which is 2 plus 1. That will be square root of 3. For the third part of this example, f of 3, the input is not in the restricted domain of the second formula nor the third formula. So therefore, we cannot evaluate at 3 for this particular functions, and we will say that undefined because there is no graph on that or no corresponding output values. So now that we know how to evaluate already, then finding out the domain. So in this case, domain of functions f will be starting from the, remember domain is always, from the least value to the largest value that we tend to write it down. So it'll be looking at x is less than -1. So it's talking about -infinity to -1 inclusive union with, okay, union with, and then the second part is what, 1 to 3. So -1 to 3. A lot of times you're going to tend to write it this way, and then that is where the mistake's going to be, okay? Because, and then lastly, you're going to say that, oh, union with 3 to positive infinity. This is not simplified interval notations, right? So that's the reason, be careful with that, because it's very tempting, and then this is what you can write it down. So what happened is, I want you to always think about this, right? When you are writing the interval notations. Like I showed to you earlier, visualize it until you feel very comfortable, and then you don't need to visualize anymore, right? So -1, that's inclusive, going to this direction. And then the second portion is -1 to 3, and -1 is not inclusive, 3 is not inclusive. And then the last part is from 3 to positive infinity. That. So if you look at, if you are talking about the domain of this, 3 parts together, we are talking about basically from this whole at -1 is filled up by this inclusive already. So we are talking about simply from -infinity to 3, not including it, and then all the way to what, positive infinity. So the domain is entire real number except what, just 3, right? So you have to very careful with, writing the simplified interval notation, not just like, translating it. So in this case, my interval notation will be from -infinity to 3, not inclusive, union with 3 to positive infinity. That will be the correct answer. If you put the other one that I write down earlier, then you'll be losing points. Okay, that simply tells me you don't know how to simplify, or you never think about it carefully. And lastly, we'll be graphing this piecewise defined functions. So let's go ahead and draw XY axis, scale them, and then try to graph it and check the answer with me. Let's pause it for a second and try it yourself and see if you can recall how to graph these or not. Okay. So the first part is absolute value shifted to the left 3 units and then shift down 1 unit. So we know that a parent graph of absolute value is like this, right? And then we're going to shift it to the left 3 units, 1, 2, 3, and then shift down 1 unit. So it will be right here like this. It's going. So, but however, we know that this graph will be restricted on a domain which is what, only less than or equal to -1. So we will be getting, 1, 2, 3, and then go down. So the vertex of this absolute value will be 1, 2, 3, and go down 1 unit, which is going to be right here. That's the vertex of absolute value. So I'm using this transformation idea to graph it, right? And then since this is an absolute value with no factors involved, so no vertical and horizontal stretching and shrinking, so I will be going, straight forward like this. But however, what you need to be careful is what it will be only up to -1. So it will be right here. That's where we're gonna stop. And then the endpoint is a closed circle right here. And then this, the left hand side endpoint is, there's no endpoint. So I will put arrowhead because it's gonna continue. Now let's take a look at on the radical, which is, this is a square root graph, right? The square root is radical functions look like this, and then it's shifted to the left 1 unit, so it's going to be going like this. And we can clearly see that it's not including -1 and then 3, so we have an open circle at -1, right here. We shifted to the left, but it's open circle at 1, and then also 3, right? It's going to be a problematic. So when you substitute 3 into here, 3 plus 1 is 4. Square root of 4 is 2. So at 3 it will be 4, but we don't include that point, so it'll be 0. And so this will be a graph like this. And once again, and you need to have this point right there, because if you don't include this, then your graph is going to be like cut, or maybe end up right here. But you are missing out every number in between 2 and 3, which is not correct, right? So you don't have a graph on this portion anymore. So this is the correct way to graph it. You need to include that 3, but need to indicate it when it's not inclusive. And to be more precise, here's another point, because when x is 0, this will be 1, right? So I have what? A curve shape like we have. So open circle, open circle. And lastly, whenever x is greater than 2, my y value is -2. Whenever x is greater than 3, my y value is -2. That's talking about what? A horizontal line at -2, and width not including 3. So it'll be open circle right here and then pointing out this direction. And this will be the graph of this piecewise defined functions. Lastly, in these sections, we want to review on how to write an equations or functions from the scratch, okay, with the given informations, which another way of saying is modeling the, the application problems with appropriate functions or equations. And the way that I taught in my pre-calc class is thinking about in parallel approach, which is 2-column approach. So one column, we're going to be looking at all the given informations, and then another column is the functions or the equations that we want to write or create, which is objective functions. That's what I mean. So in this problem, a rectangular has area of 16 meters square. That's the given. Express the perimeter of the rectangle as a functions of the length of one of its sides. So specifically say that the perimeter has to be what represent as the length of one of the sides. So let's take a look at on this. This is a rectangle. Whenever you can draw the picture, draw it. So that way you can visualize it, right? And make sure you draw it correctly. Here's a rectangle, which is the length and the width that we know. And the given part is the area is 16 meters square. And we know that the area is basically what? Length times the width. Right? Those are the informations that we have so far. So therefore, 16 is equal to length times the width. So that's on the first column that I usually put it in, which is all the informations that I know. Then what we're going to do is on the second column, we're going to start our objective function. Our objective is to write the perimeter of this rectangle with, right, as a functions with what only one of its sides. It doesn't really specifically say that which side you need to use. So starting, you don't need to write down the functions right away. You can start from the scratch like this. So we know the perimeter, which is perimeter of rectangle, is 2 times the length plus 2 times the width. But what I want is I want to write the function is one variable functions for this equation. So that means my perimeter has to be what? A functions of either the length or a functions of the width. You have to choose. And once you decide it, then you can use the information that we have in column 1 to manipulate it. So in this case, let's say if I, want to write a functions of what? The width. Then what I need to do is I need to convert this length, because I cannot have 2 variables anymore because of functions with 1 variable. So I need to somehow get or represent the length width in terms of the width. And that can be done by using the information that we have directly sometime. Okay, many times, in many occasions, we can use it directly from the information that we have. And sometimes we need to like tweak a little bit. So in this case, what we know is we know the area of the rectangle. So therefore, I can rewrite the length in terms of the width by dividing both sides by the width. So now I see that the length is 16 divided by the width. So I can substitute it in here. L is basically what? W divided by 16, 16 divided by W. So therefore, now my final answer, the width, the perimeter in terms of the width of the rectangle is going to be 32 over W plus 2W. And that will be the final answer for this problem, because we just want to express as a function. Okay. So this similar approach can be done on any type of problems when you need to start from the scratch. So let's take a look at on example number 2. A Norman window has the shape of rectangular surmounted by a semicircle. So it's talking about this picture. Here's a Norman rectangle and surmounted by what? A semicircle, meaning half a circle. If the perimeter of the window is 30 feet, express the area of the window as a function of the width x of the window. So I'm gonna say that my width right here will be x. And here's my length. And the reason why I put it that way is because that will make it easier for us to think about what is the radius of this rectangle is going to be. And we know that the perimeter of this, normal window is 30 feet. And what is the perimeter? The perimeter in this case is the length plus 2 of the length plus the width, okay, plus the circumference of the half of a circle. Circumference of the circle is 2 pi r. Half of that will be just pi r, which is equal to 30. Right? So that's what we have so far. Now, our objective is finding out the area of the window. So the area of the window is basically the area of a rectangle plus the area of a semicircle. The area of a rectangle is easy, which is length times the width. Area of a semicircle is not difficult either, which is pi r squared is the area of the whole circle, half of it. In this case, we want to indicates this area of the window with the width, which is x. So we are talking about A of what? X. So therefore, I need to know what is the length it's going to be. So in this case, my width will be x, and pi divided by 2, r squared. R is basically, the width is x right here. R is only what? Half of the width. So x divided by 2 is my r. So therefore, in here, I have my r will be x divided by 2 and squaring it. So the only thing left off is to find out what is my length going to be. And that's where I need to go back to this equations and then find it out. So this will be 2L plus x plus pi times x divided by 2, that's my radius, is equal to 3. Multiply everything by 2, which is going to be 4L plus 2x plus pi x is equal to 60. I want to clear the fractions. And then I'm going to be solving for L. So therefore, that will be 4L is equal to 60 minus 2x minus pi x. And then finally divided by 4, which will be 60 minus 2x minus pi x over 4. And that is my L. So when I substitute it into here, right, this portion, so my answer will be the area of the functions, right? Area of this window represented by the width is going to be 60 minus 2x minus pi x all over 4 times with x plus, when I simplify a little bit right here, when you square it, it will be x squared over 4. So it will be pi x squared over 8. You can simplify further, or you can stop right here. It's really up to you. Right? If you want to simplify further, then I'm going to have to make it LCD and then distribute it. So making it LCD will be 8. So 2 times 60 is 120, and multiplied by this x will be 120x, and minus 4x squared, and then minus pi x, 2 pi x squared, and then adding with plus pi x squared, and which will become 120x minus 4x squared minus pi x squared all over 8. And that will be the simplified versions. And either one is fine, on a test, because it's only asked you to write down the expressions, right? Functions, not simplifying it. But need to know how to simplify it because we want to talk about something else later on, right? To continue from this point. And this is the key things that we want to look at in this 1.1 for as a review. And the homework for every sections is indicated in the beginning of the sections notes, which is right here. The homework will be done, right? These are the homework numbers.